extremely happy to continue this morning session with the talk of Catherine Hsu from the Swarthmore College, who will tell us everything we need to know about explicit non-Gorenstein R equals T via rank times computation.
Thank you so much. So thank you, of course, to the organizers. And on a personal note, I just want to say that I started working on this project when I was a Heilbronn Fellow here at the University of Bristol. So it's special to present it for the first time back here. Feels like home. Okay, so this project is joint with Preston Wake and Carl Wang-Erickson, and it is the second paper in a series of 2 papers that focuses on the relationship between arithmetic and modular forms, particularly on the arithmetic side. And so to start, I want to start with some instances. Can we make the bar go away? I want to start with some instances of this relationship between arithmetic and modular forms that are known for prime level. So we'll be considering weight 2 modular forms.
More.
I'm going to blame this when I run over on time.
I can only end the talk.
All right, so we fixed 2 primes, P and N, and we'll assume that P is at least 5, just so we don't have to be too careful about 2 and 3. And so we'll fix usual notation where we're looking at our Eisenstein series of weight 2 and level gamma naught N. We have a Hecke action on the series, and we can look at the annihilator of it, which we call the Eisenstein series. And then we can complete our Hecke algebra at the maximal ideal generated by our Eisenstein ideal in P and look at our cuspidal quotient. So that's follows Mazur's notation. And so, sorry. Okay, and so a natural question is whether or not this cuspidal quotient is non-zero. In other words, is there a new form that's congruent to this weight 2 prime level Eisenstein series? And so Mazur gave a beautiful answer to this, which is that the answer is yes, it is non-trivial if and only if P divides the numerator of n minus 1 over 12. And he actually did a bit more. He showed that this cuspidal quotient is Gorenstein, which is a nice geometric condition that will come up later in the talk. And he showed that the Eisenstein ideal is principal and gave this very explicit criteria for whether the expression TL minus L minus 1 generates it. And so one question he left on the table was about what we can say further about the structure of this Hecke algebra. And in particular, it's a free ZP module of rank at least 1 if it's non-zero. And so the question that we can ask is, what is the rank as a ZP module? And in particular, what's the arithmetic significance of when we have higher rank versus rank 1? So that's what I mean about arithmetic versus modular forms. So some known results. So first, Morel in 96 showed that this rank is strictly greater than 1 if and only if this strange number is a P power mod L. This is called Morel's number sometimes. And then Caligari, Emerton in 05 showed that if the rank is larger than 1, it implies that the FP dimension of the P part of this class group is strictly greater than 1. And most recently, Wake and Wang-Erickson showed that if this rank is strictly greater than 1, then we have if and only if with some cup product vanishing in Galois cohomology. And so we're not really going to talk too much about item 1. The method of proof for that is very direct computation with the Hecke algebra using modular symbols. And so instead, we're going to focus on some of the techniques that come up in 2 and 3, specifically 3. And so in particular, in order to prove these results, the approach is to first establish what we call an R equal T theorem, and then leverage that for information about these objects. And so because that's the approach we're going to take, I want to just start with a little overview of what I mean by R equal T theorem. So the 2 objects in an R equal T theorem are R is some sort of universal deformation ring, and T is a Hecke algebra acting on a space of modular forms. And so if we define R correctly, then it should parameterize some arithmetic information about our Hecke algebra acting on these modular forms. And although I'm not going to talk about it much, I want to point out that that's a very non-trivial question of defining the correct R. So this is the subject of several papers by Wake, Wang-Erickson. And in fact, we need to use the pseudo-deformation machinery to have the correct R in the setting we're going to consider. And so assuming that we have an R and a T that correspond in this nice way, there's a standard argument to construct a surjection from R onto T. So we kind of get that for free. I mean, I get not for free, but I'm going to take it for free. And then so in the proof of these results 2 and 3, Caligari-Emerton and Wake-Wang-Erickson apply what's called Wild's numerical criterion to deduce that we in fact have R equal T, and then they proceed on their way. And so in particular, in order to use this criterion, we have to have that our Hecke algebra is a local complete intersection ring, or LCI for short, which is a very nice geometric property. And we can't use this method if we lose this property. And so in particular, Wake-Wang-Erickson have considered square free level cases that have this nice LCI property. And so today's goal is to outline a computational approach for establishing R equal T via a different method where we actually compute on the R side in settings when when our Hecke algebra is not LCI. And so I want to point out that we're going to be in a very specific setting where our Hecke algebra is not LCI. It's not general, because in order to get our hands on these objects on the deformation side, we need to be very specific in order to have any hope of computing. And so our starting point will be the same. We're going to start from this surjection from R onto T, but then we won't invoke the numerical criterion. That's where we're going to give a new method. And our strategy is going to be to give arithmetic conditions that guarantee that R is as small as possible. And so if R is as small as possible, then we'll force an isomorphism between R and T. Good? Okay. All right, so what is our setup? So I'll refer to our setup as Ribot's new form setting, which I'll explain momentarily. And so we're going to stick with weight 2 modular forms, but now we're going to allow our level to be divisible by 2 primes, and they'll have very specific conditions. So the first is L naught should be congruent to 1 mod P, and we're going to impose the condition that the rank of the Hecke algebra at level L naught is 1. And so this is putting us exactly in Mazur's case that he studied on the L naught level. And the assumption that we just have one old form here, the rank is 1, that's just to make our lives nice. So there's no mathematical reason why we should have to impose that. And then L1 will be a prime that's not plus or minus 1 mod P, but we will assume it's a P power mod L naught. So if you're following very carefully, you'll notice that this is the same condition that appeared in Mazur's theorem for whether or not TL minus L minus 1 generates our Eisenstein ideal. And so in Mazur's language, we want L1 to be a bad prime, so it will not generate the Eisenstein ideal. Okay, and so one more, and we need our Eisenstein series. So when we now have 2 primes on our level, our Eisenstein space will have 3 series, and we fix 1 by choosing our eigenvalues under the Akin-Lehner involution. So we're going to assume they're both -1, -1. And so now you might think that there are no additional Eisenstein congruences because the p-adic valuation of our Eisenstein, the constant term of our Eisenstein series, hasn't increased. But in fact, Ribot showed that there are additional congruences, and this is coming from L1 being a P power mod L naught. And so this is kind of what forces us into this bad, not LCI situation, which is that we have our Hecke rank is at least 3, since we have our Eisenstein series, our cusp form, we isolate one cusp form via our choice of Akin-Lehner signature, and then Ribot's new form. So those are our 3. And so you can check computationally that T is not LCI in this setting. All right, so that's the setting we're going to consider. And so the main result we state as follows. So in order to state it, I need to construct a tower of P extensions of Q zeta P. So our first level is, and I've been waiting to show this slide for a while. So our first level, we can define K explicitly. It's Q adjoins zeta P and a P root of L1. The definition of L could not fit in my little green box, so you can look in our paper or Wake-Wang-Erickson's previous work. It's uniquely characterized by conditions coming from L naught. And then their composite is this field M. Then our second level, this M prime is characterized by being a Galois extension. Its Galois group has omega naught, it's omega naught isotypic, and it's totally unramified. And the primes over L naught split and M prime over M, so that uniquely characterizes it. And then our next level may or may not exist. We're going to assume it does for its definition. If it exists, then it's uniquely characterized by similar conditions, which you can read. And so we could state the main theorem in terms of the tower M, M prime, M double prime, but it would be not so fun to actually compute the conditions in that tower because it's quite large. So it turns out that M prime uniquely characterizes this K prime, and M double prime characterizes this K double prime, and that's where our conditions will live. And so our main theorem says that if we take P L naught L1 satisfying our rivet new form setting, then if the rank of our Heck algebra is strictly greater than 3, then the following two conditions hold. All primes of K over L1 split in this first K prime over K, and there exists some prime of K over L naught that splits in both K prime and K double prime. And so in particular, if either condition fails, then we have this rejection from R onto T is an isomorphism so that R equals T. And so what's happening, so first I just want to say that the condition one, if condition one is met, then M double prime exists. So that's how we know if M double prime exists. And what you should think is that, or what I want you to take away by the end of the talk is that conditions 1 and 2 control the size of R. So if one of the conditions fails, then that means that R is small. And so by our setup, we'll be able to conclude that R equals T. But if the conditions hold, then that actually means the size of R is large. And so we are not able yet to show that we have R equal T in that case. That's why we only have one implication. But we conjecture that it is the case. And at the end, I'll talk about some computational evidence that basically, if we know R is large, we can show by computation that T is also large. We just can't prove that it always holds. All right. So I said that. Great. Okay, so where does this come from? Well, it comes from this deformation theory setup. And so I'm going to call this method R equal T via rank bounds, which again, instead of using Weil's numerical criterion, we're going to directly control the rank of R. And so following the work of Wang-Erickson, we study a deformation ring of Galois pseudo representations of our character that's the sum of the mod p split atomic character and the trivial character. And I'll just say it's not on the slide, but the 4 conditions that characterize our deformation problem is that we want our pseudo representations to be unramified outside of NP, have cyclotomic determinant, be finite flat at P, and unramified or Steinberg at L naught and L1. So you don't need to, that's going to be kind of swept under the rug, but just so you've heard the local conditions. And so this is the input that goes into the pseudo deformation machinery. So we fix our triple of primes. And so associated to L naught and L1, we can fix 2 specific co-cycles. So B1 is the Kummer class of L1 in our cohomology group, and C1 is a non-trivial class that's ramified only at L1. And once we fix these 2 co-cycles, we can show, well, Wake, Wang-Erickson show that their cup product vanishes because L1 is a P power mod L naught. And this means that they're the co-chain that satisfies this boundary equation. And so then if we define D1 via this expression, we can check for a co-chain B2 satisfying this boundary equation. And so in particular, the existence of B2 corresponds to the existence of M double prime. So they're going to be the same. And so this is a lot of notation. What you should take away is if you're wondering about our naming convention, these are actually coordinates in a general matrix algebra, in a GMA representation. So we have like A, B, C, D. So that's what the lettering comes from. And then superscript 1 means it's a coordinate in a first order deformation. And a coordinate, the superscript 2 means that it's a coordinate in a second order deformation. So that's kind of how we're keeping track of our data. And so all I need you to extract from this is that we have these 2 cochains, A1 and B2, and that's what we're going to need. So the theoretical output from the first paper in the series is that the FP dimension of R mod PR is strictly greater than 3 if and only if these 2 invariants vanish. Alpha is associated to A1 and beta is associated to B2. And so basically these cochains are controlling these 2 invariants. And so these are the conditions in terms of the deformation theory that control, this is what I mean by we're computing explicitly on the R side. These conditions are what control the size of R. And so what made us think that this paper might be relevant to this conference is that we compute these conditions, which is a very non-trivial question of how to actually compute whether these hold or not. Okay, let me make sure. All right, so how do we go from theory to computation? So we have these 2 special cochains, A1 and B2. And the key idea is that we want to restrict them to some number field where we can then leverage Kummer theory to start doing actual computations. And so we restrict them to K, which you recall was this Q adjoint zeta P, comma, the P root of L1. And so we take a 2-step approach that kind of mirrors how you might approach a boundary value problem in like PDEs. So first, we want to find what we call candidate cochains that solve those two differential equations that I had up a slide ago. And then we're going to adjust them so that our candidate solutions satisfy the local conditions coming from R that I said quickly but didn't write down. Okay? And so if we can succeed in computing these S units, then the picture we get is that we can adjoin a p root of that S unit, and we can generate this Kummer extension K prime and K double prime. And so under this correspondence, we get an equivalence between these two sets of conditions that you've seen now. So you've seen it in terms of Galois cohomology and in terms of our number fields. And so the goal for the rest of the talk is actually to give explicit formulas for how we compute these S units. And so then the idea is that we can actually do all of our arithmetic in the number field K, which is accessible via Sage. Okay, any questions? Okay. All right. So how do we compute a unit? We need to compute these two S units, one for A1 and one for B2. And so for A1, well, it comes from a complete reinterpretation of what this boundary equation means. So any cochain at all that satisfies this boundary equation, it'll actually cut out a degree p cubed times p minus 1 twisted Heisenberg extension. So it's Galois group is Heisenberg. And it's cut out by this representation. And so in particular, if our cochain also satisfies the local conditions, then it will exactly cut out M prime. So just from the boundary equation, we don't necessarily get M prime specifically, but with our conditions, our extra conditions, we will. And so recognizing this relationship between our boundary equation and this Galois problem, we now can use Sharifi's theory to give a formula for how to compute this. So it's in terms of a Kolyvagin derivative operator and this gamma that satisfies, whose norm is our special cocycle, the unit for C1. And so what's quite nice about this is that if you can imagine we have S units for all of these objects, then it's quite easy to compute this formula. And then our local adjustments can be written in terms of a power of zeta p and a power of, I'm not going to talk too much, but that's another S unit A naught. And these correspond to our finite flat condition and our unramified or Steinberg condition. And so that is how we handle our first S unit. Oh, and I wanted to mention that in addition to this being very computable, one nuance, I guess I'm glossing over several details, but one detail that I can say with what's on the board is that the Galois action that we need on this S unit has not been encoded in this formula. So that's another condition that we need to impose as we're computing. Okay, and so now we want to compute, we play the same game for B2 restricted to GK. We have a more complicated boundary equation, and so we get a 1 degree higher twisted Heisenberg extension. And again, if we have all of our local conditions met, then this will cut out M double prime over Q. And so we get a more complicated formula here. So it's still in terms of these Kolyvagin derivative operators, but to give you a little bit of idea of where it's coming from, if we look at this triple Massey product, B1, C1, B1, you can notice that those are the entries along the off diagonal in this matrix. And so just as a cup product kind of contains the information about whether or not we have this cochain in our upper right entry, you can view this as two overlapping. So the upper 3 by 3 and the lower 3 by 3 overlapping representations. And so that's the data of this triple Massey product. And so there's a middle step I'm leaving out, which is that we have to relate this triple Massey product to one of the form B1, B1, C1, which is called cyclic. And so that's where our formula in terms of a Kolyvagin derivative operator comes from. And then similarly, we have our local adjustment. This time it's in terms of we have to multiply by a power of P and a power of L naught. Okay, so we have lots of computational evidence for R equal T. So we've attempted to verify whether our conditions in the main result hold for the triples with P equal 5 and P equal 7 in these ranges, which are reasonable. And so in particular, what we have found is that in every example that our algorithm is completed, so I'll say a moment what I mean by if it's completed on the next slide, we have either found the second bullet point that condition 2 is not satisfied, and so we know for sure that R equals T, Or we have verified that 1 and 2 are satisfied. So we know that the FP dimension of R mod PR is strictly greater than 3. And we've computed using modular symbols that the Hecker rank is also strictly greater than 3, which is, we're saying it's evidence that we have in fact constructed the correct R to match this. Okay, so I end with just a few points about our implementation and stage. So the program for the conditions is available on GitHub, and it really just heavily uses the S-unit interface that was written by John Cremona to the unit S-unit groups that are computed in PARI and GP. And I'm a beginner coder, so if anyone has suggestions for how to make it, more official and robust, I'd be happy to hear them. But you can take a look. And so all of our computations are carried out either at my home institution of Swarthmore on our Strelka computing cluster or the SMP cluster at the University of Pittsburgh. And so we just arbitrarily gave a computation 3 days to run. And so if it didn't complete in the 3 days, then we filed it under did not complete. But I imagine a lot of them would complete if we gave them more time. So a particularly interesting computational observation is that condition 1 in our main result is always satisfied so far. And we've actually checked that in a much wider range of examples because it's quicker to check. And we can't explain it. So we're hoping that in future work that we can either explain from a theoretical point of view why this condition is not really a condition to check, or find an example where it fails. But so far it's just this mysterious computation. And then the last thing I want to say is that when going from these abstract, conditions on our R side to actual computable conditions, it took us many tries to kind of find the right home for where to do our computation. And so in fact, we first tried to work over M, but that's quite a large field and it was too large. And so then we actually tried L, which is the counterpart to K. But it turns out when you restrict these cochains to L, it doesn't work either. And so we finally landed on K. But a lot of the difficulty in this project has been on making all these little fiddly things work at the same time. But if you zoom in on any one specific part, I think you'd be like, oh yes, this computation is, straightforward. And so now I will really end with just to give you a flavor of how the program works. This is our first example. So 51123, its counterpart is 51143, where you'll have rank at least 4. But I thought it was more fun to give you one where R does equal T in fact. And so you can see that all of our computations are just in terms of these S units that Sage spits out. And so for each one of these arrows, there's an algorithm that you go from. So we start from this C and gamma that cuts out our L field, and then we have our candidates, and then you see a local adjustment, and then we can check our condition. For the left columns A1, the right columns B2. And so in our paper, we have lots of tables of data. It's probably meaningless if you don't look at the context, but I thought it would just be nice to give you an idea of, how the algorithm kind of works. Okay, I think I made it on time.